Hello. Today we're going to go over volume of prisms and cylinders. This won't be too hard. Chances are you've got an idea of how it's going to work anyway. Well, the first thing we're going to start with is a cube, which technically is a prism. You could say, well, you could pick any pair of sides. Pardon me. You could pick any pair of faces, and they would be congruent and parallel. I guess you could call it a square prism. Anyway, but not quite, because a square prism could have different links connecting the two parallel faces, whereas these, every single face is congruent to every other face. And the volume of a cube is s cubed. That's all there is to it, which is maybe why we say cubed when we put a 3 up here on top, just as the area of a square would be s squared. Pretty easy, right? When we work some problems, a couple of things you'll have to know. Let's see here. If we have two polyhedra, say P1 is congruent to P2, that means that the volume of P1 equals the volume of P2. Okay. It's pretty easy. You'd have probably guessed that anyway. It's also true that if we were to break this up into smaller cubes or prisms or pretty much anything else, if we broke them up into shapes which completely covered the volume and didn't leave any spaces, then we could add them all up and get the original volume. Just like with the area formula. In other words, if you add up all the small volumes that make up the larger one, you will get the larger one. It's exactly what you would expect. For instance, if I put a rectangle on top of this that extended out but had the same width here, I could compute the volume of this whole thing by taking the volume of the rectangle on top and the cube on the bottom, add them up, and that's the whole volume. And that's all that you need to know. It's pretty simple. What about something that's not a cube? Well, here we have a rectangular prism. Actually, it might even be a square prism. I'm not sure about these rectangles on each side. They may or may not be squares. For what we're doing, it doesn't matter right now. Notice that when we cubed this, we could also write this as, say, a sub b, area of the base. Well, we could write the area of the base times s, because s is the height. We could have written it this way. And what would the area of the base be? Since this is a square, this would just be s squared, and we end up with s cubed. Over here, the same thing. If we have area for a base here and some height, then we can write that the volume is the area of the base times the height. And of course, if we call these, say, L and W, like length and width, very clever original names for these two dimensions, then we could just write L, W, H. Keep in mind, just like over here, volume measurements are always going to be units cubed. If you don't get units cubed, you've made a mistake. You can't have inches squared as a volume, or inches. Also, inches to the 4th power won't work either. It's got to be to the 3rd power, and that's it. That's for your units. I'm not trying to tell you that every number will get cubed. No, of course not. All I'm saying is whatever units you use to measure these, in the end, for a volume, you're going to have to get units cubed. And if you don't, then look for your mistake. Well, for a cylinder, I bet you can guess what the formula is going to be. If we have an area for our base down here, and a height, well, guess what? Volume is going to be the area of the base times the height. Well, what is this base? And keep in mind, area is always in square units, so same thing holds here. We get units squared for the area times units, whatever they are. For instance, if these were inches, you get inches squared times inches, and you'd end up with inches cubed. Well, this part is just pi r squared. That's where the inches squared would come in, and then h. That also equals the volume. Pretty simple. Now there's one other thing you need to know. It's kind of weird, but it's cool. Hang on, and I'll show you. Suppose I bent this cylinder over like this. Suppose that h over here is exactly the same as the distance. We just drop straight down. This vertical distance to this plane, if this is also h, and if this is also r, the fact that it's slanted doesn't matter. That's kind of weird. It's called Cavalieri's principle. And what it says, really, is that if each cross-section is the same, then, and the height is the same, then the volume's going to be the same, even though they don't look like the same object. This over here should have had an R in it. And the point is, this H and this H are the same, this R and this R are the same, then the volume of this thing and this thing are going to be identical. When you take a cross-section of this, even though they're stacked off to the right a bit, in other words, if you took a cross-section, you've got a side view of a circle, say, and another cross-section, but it's just off to the side a bit, and another one. Well, when you add all these up, does it really make any difference that we didn't line them up perfectly like this? After all, every single one of them is exactly the same length. If we add a width to them, like that, and keep going, where this one is smaller. By that I mean it starts off to the right and it extends farther to the right and on down. If we were to do that, there'd be no difference between adding these up or adding these up, whether they're stacked up right on top of each other in such a way as to look like this and form a stack that won't eventually fall over. That's what looks so weird about this, because nobody would ever stack anything like this. If you had a whole bunch of discs, say CDs, well, you know the thickness of the CD, so you can compute the volume. And the point is, if you stack them up straight, just like a cylinder, or stack them up staggered off to the right so that it forms this leaning tower of CDs, the volume will be exactly the same if you've got 100 CDs stacked up this way, or you stagger them off to the right a little bit. You still have the same volume. The difference is they would probably fall over before you got to 100, because when you do it this way, they don't stay up very well. So the straight cylinder is more stable, but that doesn't affect the actual volume. So as long as the height is the same and the cross section would be the same, then you've got the same volume. So each of these would have exactly the same volume. That seems counterintuitive, I know, but it works. And maybe this is a better way to look at Cavalieri's principle. Suppose these were, say DVD cases. You could stack them up straight, or you could stack them up offset. It's exactly the same number of CDs. So the volume would be identical. The only difference is you've staggered each one off to the right a little bit so they don't stack up straight. But The fact that they don't stack up straight doesn't mean that they're going to change the volume any. After all, you got the same number of DVD cases either way. And as you can see here, the height is exactly the same for each one. The fact that you stagger them off to the right, it really doesn't matter. Now let's take a look at some problems now. Describe and correct the error. Well, let's just find the volume of a right cylinder with these dimensions. Radius 4 feet and height 3 feet. Remember, a cylinder, that's just the base. Pi r squared times the height. So what did he write? Well, gee, this doesn't look right at all, does it? What you want is pi r squared, not 2 pi r. Everything else is okay. What he did was take the circumference and multiply it by the height. That would give you the lateral surface area. It would not give you the volume of the cylinder. What we need here with a radius of 4 feet is pi times 4 squared, which is 16, times 3 feet. Remember, the 16 is feet squared. And this is feet. So the whole thing is going to be, what's that, 48 pi feet cubed. Yeah, it just kind of messed up in here. It's pi r squared, not 2 pi r. We want the area of the base, not the circumference. And here's one that shows that volumes can add and subtract just like we did with areas. For instance, we got it's like a rectangular prism cut out of another rectangular prism, really, although a lot of people would just call this a box. Doesn't matter. Whatever we call it, let's call it a rectangular prism, since that's what we're working with these days. It's 12.4, 7.8, and 9. So all we have to do is multiply these to get the total area of the prism, and then we're going to subtract off this other rectangular prism, just like we did with areas. And you can always do that with volumes, just like you did with areas. So if we do that, just take the volume of the large rectangular prism. That would be 12.4 times 7.8 times 9, and we get this here. And then take the volume of this smaller one in here. It's also a rectangular prism. Same height, 9 feet. Multiply this out and get 48.6. We subtract the small one from the big one, and the actual total volume is 821.88. Simply had to apply your volume formula for prisms. Well, rectangular prisms. Really very easy. With luck, you get lots of these kind of problems on your state exam. Well, here we're given the volume ahead of time, and we have to find one of the dimensions of the cylinder. What is the volume? Well, by now, we know it's pi r squared times the height. And let's see, they gave us that the volume is 64 feet. Pardon me, 64 pi cubic feet. And we have a radius of 4 feet. 4 squared times h, which we don't know yet, but we can divide through by pi. Cancel those, and 4 squared is 16. If we divide through by 16, we should get 4 over here, h over here. And now it's right over here, choice A. So once again, just you see stuff like this, set up your basic equation and see what starts to drop out. this case it was real easy. As long as you set your equation up right, you can instantly spot all kinds of stuff to cancel and divide, and just about do this in your head. Here we have a prism with rhombuses on each end, and of course, like all prisms, they're connected up by rectangles. So for the prism, once again, all we need is the area of the base, put it over here, a sub b times the height. They gave us the dimensions, well, the diagonals for the rhombus. That's convenient because that's an easy way to get the area of a rhombus. Remember, for a rhombus with diagonals d1 and d2, the area of a rhombus, say a sub rh, is 1/2 d1 times d2. In this case, the area for the base, which is a rhombus, is going to be 1/2 12 times 16. The height of the prism is 8 meters. And of course I'm doing this problem backwards. Since this section is on volumes, I thought we'd do the volume first. Make sure we got a good handle on that. So we get 1/2 times 12 times 16 for the area of the base times the height. That's 768. That's the volume. It's this one here. And we'll go backwards and do the others. If it's 8, the height is 8. Well, getting the lateral surface area is pretty easy if we know the length of one of these sides. Because for the prism, these two rhombuses are parallel and connected up with rectangles on each side here. So we need to know. We need to figure out S. And from the properties of rhombuses, we can remember that the diagonals are perpendicular, although they don't look it in this drawing. Sorry, it's not a very good rhombus. And they bisect each other. So if this is the long one, that means this is 8. And 8, and this would be 6 and 6. So we could find these pretty easily, because if these are the two legs, this is the hypotenuse. So all we have to do is take our 6 squared plus 8 squared, 36, plus 64, and then take the square root of that. Well, gee whiz. 64 and 36 is 100, so the square root would be 10, unless I made a careless mistake. Well, the lateral surface for one of the rectangles connecting up these rhombuses would be 8 times 10. And we need 4 of those. So and if we multiply this out, we get 320, and this would be meters squared. And up here for volume, I really should have written meters cubed. 768 meters cubed equals the volume. Down here, the lateral surface, that doesn't include the base surfaces of the two rhombuses. That's just the lateral surface. That's the rectangles that connect up the parallel faces, which define the prism. Well, we've got the volume, and we've got the lateral area. Now the entire surface area would just be the lateral area plus the area of the two bases. We've already got that. Lateral surface area is 320 square meters. Now for the rhombus, this part here, 1/2 12 times 16, that's the area for the rhombus. So we can write So for the total, we can write it out this way. We've got the area for the rhombus times 2, because there are 2 of them, plus the 320, because we've already worked out this part, the lateral area. So this is going to be, these 2's will cancel, you get 12 times 16 plus 320. So for the total surface area, whoops, that's not cubed, that's squared. That is the total surface area. 512 square meters. So for this problem, it was really pretty easy. We just had to go back and remember our earlier sections on lateral and surface area, and then volume of a prism, which is also fairly easy. Remember, these are all practical formulas, things that you might actually use in everyday life. Not just being an engineer or a scientist or a mathematician, but being somebody who needs to put up curtains or buy bed sheets and needs to know what size, or fill up an aquarium. You know, this is all real practical stuff. Yeah, this problem is interesting. I think it's interesting. I never heard of the blue hole. Well, until now, of course. Say it's 400 feet deep. Well, for ocean depths, that's not really all that deep, I guess. Doesn't seem like it to me. And about 1,000 feet wide. And they say we're going to approximate it as a cylinder. And I want to know what's the volume of this blue hole. Well, it's 1,000 feet wide. That would mean the radius was 500 feet, wouldn't it? And it's 400 feet deep, so we just use our pi r squared, the base, times h. So we get pi times 500 squared times 400. Now, they probably taught you scientific notation back in Algebra 1. It's pretty easy. Just put things in powers of 10, that's all it is. It can be a quick way, especially if your calculator goes dead, you need a new battery or something. This is real handy. You write 500 as 5 times 10 squared. And then square that. You write 400 as 4 times 10 squared. And of course pi is just pi. But when you square this, you get 25. 10 squared is 10 to the 4th, right? You just bring the exponent in and multiply it here. In other words, 10 squared is 100. 100 squared is going to be 10,000, or 10 to the 4th power. Over here we have 4 times 10 squared, still. And this is all times pi. 4 times 25, that's 100. We'll put the pi out there first. And 10 to the 4th times 10 squared is 10 to the 6th. So that's going to be pi times 100 with 6 zeros after it. But if I use 3.14 for pi, then I get 314 million. If you use the pi button on your calculator, you'll get a whole bunch of other stuff out here, because pi actually has more than 2 places past the decimal. And now you see the difference between approximations. I should probably do that and show you what the actual answer is. If you use the pi button on your calculator, which has pi out to, I forget how many places, 10, 20, something like that. So here's what happens when you use 3.14 for pi. And here's what happens if you actually use the pi button on your calculator. about 150,000 off. Whether that's important or not, who knows? I mean, 150,000 does seem like a lot. On the other hand, when you compare it to 314 million, not that much, is it? What about how many gallons? Well, if there's 7.48 gallons in 1 cubic foot, well, here's the number of cubic feet right here. So all we have to do is multiply this by 7.48, and we've got the number of gallons. Now let's separate this. This is going to be a real simple equation here. We just need the volume. I'm just going to write it as V. It's either one of these great big numbers here, times 7.48. That'll give us the number of gallons. So we've got this many gallons. It's about 8 pounds per gallon. So how much would this blue hole weigh? And here's where scientific notation comes in real handy. Because when you take this huge number and multiply by 8, it's just too many numbers. So you write it as 1.89 times 10 to the 10th. And if you remember, if they showed you that in Algebra 1, that means there's 10 zeros after the decimal point, or 8 zeros after the last significant digit here. That's a lot. That's like an 11-digit number, and that's too big. So you just write it this way, 1.89 times 10 to the 10th. That's heavy, and it makes you wonder why the Earth doesn't wobble. And just for fun, if you want to, try to figure out the volume of the ocean and what it weighs. But this problem was actually, again, pretty easy. It's very practical. You're just computing the volume of a cylinder. And volume equations are very practical. You frequently have to figure that out. Once you've got that, they just, out of curiosity, said, how many gallons would that be? That would be a whole lot, wouldn't it? But overall, pretty easy problem. Well, this one seems fairly practical. People have aquariums. They give us the dimensions. We're going to fill it 3/4 full. And due to the way water flows, I don't think we can put it all on the left side or the right side and leave 1/4 on the left empty. I think it's the top part that's going to have to be empty. The top 1/4. So the height 3/4 of 20 is 15 inches. So let's put that in here. 15 inches is how high the water level would be, but it's still going to be 30 by 10. So this is pretty easy. We just have to write 30 times 10 times 15, because it's only 3/4 full. So if we multiply this out, we get 4,500 cubic inches. Now, when you submerge a rock in the aquarium, the water level rises 0.25 inches. Find the volume of the rock. Well, they're assuming that you understand Archimedes' principle, which is that if you submerge something in a body of water, the amount of water you displace is exactly the same as the volume of the thing which you put in the water. People probably knew that before Archimedes pointed it out. After all, they're not giving you Archimedes' principle here, but they're assuming that as a bright American teenager, you would just recognize that instantly, even though you may never have heard of Archimedes' principle. So what we have to do, we could do it both ways. We could take it, we've already figured this out, now we could figure it out with a water level of 15.25 and then subtract the 2. But that would be the same as figuring out what the volume is of say, a thin slice of water that was 30 inches long, 10 inches wide, and 1/4 of an inch high. Let's do it that way. So, if we assume that the volume of the water displaced is exactly the same as the volume of the rock is 75 cubic inches. Now, they want to know how many rocks. Just like that, you'd have to drop into the aquarium before it spills out. That sounds like a fun experiment, especially if you've got a nice carpet you can ruin. But let's do it on paper instead. What have we got? Well, how much room do we have? In other words, how much volume is left over when it's 3/4 full? Well, the answer is 1/4 of the tank is left over. And just as 3/4 was 15 inches, the last quarter of the height would be 5 inches. So the 5 inches from the water level to the top of the tank is what's left over. So that's how much volume we haven't used. That's how much the aquarium could hold, but we haven't used yet. We could do it that way. We could also take advantage of the fact that this equals 3/4 of the volume. We can do it either way. Let's try it this way first. We get 5 inches times 30 times 10. And what we get is 1,500. And that's cubic inches, of course. The question is, how many rocks can we put in before we displace 1,500 cubic inches? Well, we would just take the 1,500 and divide it by 75. That's the volume of each rock. And that equals 20. So we can drop in 20 rocks, and that'll bring it right up to the edge. One more, and the water starts to spill and destroy your carpet. Suppose we did it the other way. We didn't really have to use this equation. If this equals 3/4 of the volume, we can write 3/4 of V equals 4,500. If we did it this way, we would get that 1/4 of V equals 1,500. After all, you just divide through by 3 now, or you could have done it over here actually. And you get V over 4 equals 1,500, which is what we were looking for. We wanted 1/4, that's the part left over, and you'd get 1,500 that way also. These are both pretty simple. They used easy numbers here. If these numbers weren't so easy, this would probably be the quicker way to do it. But this was 5.3, 33.7, and 11.9. Well, then I would use this, because it's much easier just to divide through by 3. Other than that, again, these are pretty easy. We just had to take the volume of a rectangular prism and some simple calculations. By the way, as long as we're doing this, you should keep in mind cubic feet, cubic inches, cubic meters. And that would work like this. Suppose they asked you how many cubic feet this was. How many cubic feet in a cubic inch? Well, let's reverse that. How many cubic inches in a cubic foot? Well, consider a cube. I guess let's make it bigger. And let's make it a really badly drawn cube. A cube drawn by someone who's never seen a straight line. There we go. There's a cube that got sat on by an elephant. Now if it's 12 inches here. 12 inches here. And And of course 12 inches this way. So how many inches is this cubic foot going to be? The volume is going to be 12 times 12 times 12. Inches, 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 or 12 cubed feet. And that'll be cubic feet. Or, wait a minute. That's inches. Pardon me. This is 1 cubic foot. Or 12 cubed. And what is 12 cubed? So 1 cubic foot is quite a few cubic inches, isn't it? So if we wanted to, we could figure out how many gallons it took to get this aquarium 3/4 full. Because the previous problem told us that it was 7.68 gallons in a cubic foot. So if we were to take this number here and divide it, we get a number a little under 3. If we divided it by 1728 and then multiply that by 7.48, and what do we get? 24, 25 gallons, something like that. It kind of makes sense. I think a standard aquarium would hold that much. So if I put that in my calculator and get that the 4,500 cubic inches translates to almost 20 gallons, about 19 and a half. And if that's 3/4 of it, then the whole thing would hold a little over 25 gallons. I don't know how full you normally. I think aquariums are usually pretty close to the top. So that'd be quite a few gallons of water. Suppose it was 25. Multiply that by 8. 8 pounds per gallon. That's 200 pounds. Think about that next time you fill an aquarium. How many gallons it's going to take? Multiply by 8. Make sure the table you put it on is pretty strong. A folding table, well, might just fold right up when you put a good-sized aquarium on top of it after you fill it with water. Water is very heavy. Long time ago, there was something called a waterbed. They were real popular. The mattresses were some kind of watertight material, and they were filled with water. Kind of fun to bounce around on it. Other than that, it was kind of a passing fad. The problem is, all that water weighs a lot. You figure out a mattress. Suppose, let's see, a lot of mattresses are like 72 to 6 feet long, and I think a big one is maybe 4 feet wide, and I suppose it's kind of thick, say 3/4 of a foot. Now, just for fun, you want to find out what your waterbed would weigh just from the water? 18 cubic feet of water. 7.68 gallons per cubic foot. 8 pounds per gallon. Well, we've got over 1,000 pounds. That's a pretty heavy bed. You can understand why some apartment buildings don't allow water beds. In fact, maybe you can understand why this was sort of a hippie fad, made popular by people who spent more time smoking weed than doing math equations, because that's just way too heavy for a bed. Most floors aren't constructed to just have 1,000 pounds sitting on them indefinitely, especially when you throw in a couple of people. Suppose you got some heavy-duty people sleeping in there. A couple of 300-pound people. Pretty soon you've got almost a ton just sitting on an ordinary floor. That's quite a bit. So based on this, I would definitely stay away from water beds. You'll probably just end up watching it crash through your floor. Well, that's about it.